Over the past few months, I have accumulated a lot of these crappy empty disposable cigarettes. Human stupidity means that they get thrown in the bin, even if they still have a nice rechargeable battery inside. In particular, a friend of mine has given me many of these electronic cigarettes. Inside I found these mysterious very thin rechargeable lithium batteries that you may have seen in a previous video of mine. Now that I have about 30 of them, today I want to try and build a 100-watt battery pack without blowing up my lab. Enjoy the video and be sure to subscribe to the channel. Let's start at the beginning. This is the module I will be using in the video. It has an honest price and has many features. For example, it has 5 USB ports and can deliver a maximum power of 100 watts. It has a bidirectional Type-C port that is compatible with almost all fast charging protocols. During the video we will learn a lot about this module. The real enigma of this project is these batteries. In fact, as in the previous video, I could not find a datasheet or technical specifications for these batteries. This worries me a bit because in order to make a safe and functional battery pack, we need to know what current these batteries can handle. Let me explain. There are different versions of this power bank module. I bought this type, that is, 100 watts total, powered by 5 cells in series. Since my batteries have a capacity of only 310 mAh, I would like to use as many as possible in parallel. I think the schematic is more self-explanatory. As you can see, the battery pack consists of 5 groups of 4 batteries in parallel connected in series, for a total of 20 batteries delivering 21 volts. Oh my god, I hope I explained everything clearly in my robot voice. It is time to clean the desk and check all our batteries with the multimeter. I spent all of last week charging them with this 1TP4056 module. Check out my previous videos to learn how to change the charge current. I charged them all to 4.2 volts and let them rest at least overnight. I want to select only those that have a voltage between 4.1 and 4.2 volts. If the voltage in some batteries has dropped, I prefer not to use them because they might be damaged. This one is okay. This one is okay. This one is not okay.
2 hours later.
After this fun activity, I have to remove the useless Kapton tape from each battery. And of course clean the contacts of each battery. Guys, these repetitive jobs are very boring. As soon as I become a billionaire, I will buy an army of humanoid androids to do all these repetitive tasks for me. Subscribe to my channel and use the referral links in the description so I can buy an army of robots. Done. Now I have a lot of tape confetti. Now it is time to solder all the batteries. Usually to solder lithium batteries you use a spot welder, which is very cheap nowadays. I don't have one, so I thank PCBWay for sponsoring this great board. Remember, PCBWay is cheap, professional, and most of all it supports young makers like me. So let's support PCBWay. In the description you will find a discount for you. Here are the PCBs. They look nice, clean, and well made as usual. The schematic of these boards is nothing more than what I showed you before. I designed 1.6 to 3.5 mm tracks to handle the currents, and the battery footprint is a custom design. At first glance, the footprint pads seem adequate for my 09500 battery. The soldering area is more than sufficient. In fact, I made the pads very large to be able to solder most disposable e-cigarette batteries. I also made sure that the contacts of the battery pack and the power supply module are as parallel as possible. The time has come to solder the battery pack. I can't wait. I start to place tin on all the pads.
2 hours later.
And now I solder the batteries, trying to center them well to the board. The contacts, especially the ground, are very wide, so the soldering iron has to be at a high temperature and takes a few seconds to melt the tin. I start soldering the batteries in parallel pairs. This way the two cells will balance their charge voltage. Making groups of 4 batteries in parallel could produce higher currents during balancing. While you are watching me solder all the other batteries at lightning speed, I would like to share some observations about this step. 1. It took me longer than expected to solder all the batteries onto the board. This is probably because my soldering iron is old and cheap and has not been holding the temperature very well lately. 2. The pads and tracks are very large and need time and soldering iron power to heat up well, so remember to raise the soldering iron temperature above 350 degrees and be patient. 3. The quality of the final welds is not very good. Surely using a nickel strip and a spot welder would have made the job cleaner and faster. The main cause, in addition to the above, is that the contacts of these batteries seem to have a plastic membrane near the central body, and during soldering this material sometimes melts away, contaminating the solder. The soldering is not very nice but seems to work. Now I just have to balance all the batteries overnight. Good morning. Let's see if the battery pack voltages are adequate. 20.8 volts. Perfect. All batteries look fairly charged. Now it is time to get the cables and connectors and connect the battery pack to the board. I install a 4-pin JST connector. The pins are very close together. Be careful not to short the pack. And now I install a connector on the power bank module. Now I should just plug in a connector to test the power bank, but in the back of my mind there is still some doubt. Before I continue with the project, I would like to ask my artificial friend a question. I have a 5S4P battery pack consisting of 24.2 volt lithium batteries delivering 100 watts. How much current should each cell deliver at full power? My artificial friend says that each battery should deliver up to 1.19 amps. Definitely a lot of current for a crappy 310 milliamp battery. Thanks for the information, my fake friend. Maybe limiting the power to 65 watts would be a good idea? My friend says you would need 780 milliamps per battery. That's still a lot of current, but being under an amp makes me feel more comfortable. All that's left is for me to wish my friend a good night.
You're welcome, human friend. Sleep well and dream of fully charged batteries. Good night.
Reading the documentation of our board, I found that by changing the values of resistor R20, we can change the maximum output current. These are the reference values. I decided to use 60 watts. Since I did not have an 18 kilo ohm resistor, I used 2 resistors in parallel. 120 kilo ohm and 168 kilo ohm. With the soldering iron at the right temperature, I remove the R20 resistor. Since I don't have an SMD resistor, I solder 2 green wires to the resistor to make soldering easier. Thanks to my trusty octopus, the work is clean. With this modification, we limited our circuit to about 60 watts. Now I feel safer and can connect all the terminals of the battery pack to the power bank module. I decided to solder the 2 main poles of the battery pack because I did not have a suitable connector. Now everything seems to be connected well. The only thing left is to test it. Let's start charging our power bank. The display lights up. A good sign. With my friend Emiliano's thermal camera, I checked the temperatures to avoid an atomic explosion. The batteries are around 28 degrees. The charging circuit is around 37 degrees. These seem like optimal temperatures to me. As a first test, I plug in my old smartphone. It seems to charge properly, but does not seem to trigger a fast charge. The circuit temperature is still around 37 degrees Celsius. I plug in the tester to find out the charge current. It's really low and I don't like it. The current is less than 500 milliamps and that seems very strange to me. Perhaps the battery voltage is too low? I don't think so. After several tests, I changed the USB-C cable and the results improved. It is now charging at about 15 watts, more than 2 amps. Being an old phone, I think this is the maximum charge. The temperature went up a bit, but that is normal. It went up to about 44 degrees Celsius. Before we move on to more intensive testing, I want to check with my USB tester what the maximum power of this power bank circuit is and what charging protocols it supports. The maximum power analyzed is 63 watts, very close to the 60 we set with the R20 resistor. It also supports pretty much all protocols except QC 2.0 at 20 volts and Huawei SCP. Nice. The next test is to connect my new SMD soldering hot plate. For this machine it is recommended to use a power of 65 watts. I set the temperature of the hot plate to 219 degrees Celsius. I start it up. Immediately the power is just over 50 watts, with a voltage of 19 volts and a current of 2.7 amps. After a while, the current and power drop, but the voltage stays at 19 volts. As expected, the power output of the power bank drops as the temperature of the hot plate rises more or less constantly. The battery pack's temperature is always perfect. After 4 minutes, the hot plate failed to warm up completely at the end of the test. It remained 3 or 4 degrees below the threshold. It is difficult to determine whether the problem lies with the batteries, cables, circuit, or hot plate. At this point, I want to test whether I can charge my PC with this setup. As you can see, the power bank is currently supplying my PC with about 50 watts of power. I will start a rendering to increase the processor's power consumption. Now, the power bank is delivering between 55 and 56 watts. Wow! That sounds pretty good to me since we're practically at 92% of the 60-watt maximum power setting. After these 2 empirical tests, I would like to try using this power bank at full power with a more rigorous method. First, I will solder the original resistor, R20, to restore the circuit to its full 100W power. For more serious testing, I purchased this 150-watt, 20-amp DC electronic load. In short, this tool simulates a load and displays various information, such as voltage, current, and power. It can also be used to test the capacity of a cell or battery pack. Finally, we will need this useful board. Setting the correct sequence of these 3 switches will allow us to trigger our preferred USB-C protocol. For our test, we will program a maximum voltage of 20 volts to deliver maximum power. Let's connect our new tools at lightning speed. As soon as I plug in the cable, the voltage rises to 19.8 volts. Fantastic! That means our new purple module is working. I set the load to 4 amps of current. As you can see, our power bank easily delivers an impressive 76 watts. Very good result. In order to reach 100 watts, we need to test at 5 amps. For now, I'll set the current to 4.5 amps. Beep, 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 beep. Unfortunately, the voltage drops at this current, so the maximum power output is much lower. Only 60 watts. What a disappointment! We can safely say that our power bank's maximum power output is approximately 76 watts. At the end of the video, we will discuss the reasons why we could not deliver 100 watts. However, I have another idea now. My wonderful sponsor, PCBWay, sent me another board. PCBWay, PCBWay, PCBWay. Discount in description. As you can imagine, the design is the same as the previous one, but it has been adapted to connect the more practical and popular 18,650 batteries with these convenient battery holders. The process is identical to the previous board. Solder the connector. Haircut the connector. Place tin on the battery contacts. Finally, solder the 5 battery holders. Look at how beautiful it is. 5 more battery holders can be mounted on the back, but I don't have them now. For now, I'm protecting the unused contacts with electrical tape. I found these 5 batteries in my inventory, cannibalized from medieval laptops. I just need to add our power bank module to finally test this board. I desolder the battery pack poles and disconnect the rainbow connector at lightning speed. Then, I reconnect everything and plug in the batteries. I leave everything on charge for several hours and check back later. Good morning. The display shows that the batteries are fully charged. Now, we can plug in our new tool and test out this power bank made from really old batteries. I'd say they're at least 10 years old. As you can see, I set the load to 4 amps. If all goes well, this setup will produce at least 76 watts. Everything is ready. Let's go. But look! Only 67 watts, and there's a big voltage drop. These batteries can't even deliver 4 amps, what a disappointment. The good news is that I now have all the data I need to draw conclusions. I learned a lot from this experience, and I enjoyed making this video. Now, the question we are all asking is, why couldn't we deliver the full 100 watts from our prototype? There are many answers. First, I don't think the problem is this module. In fact, it has always worked well and delivered the expected results. The main cause is certainly the batteries. In the first case, when we used e-cigarette batteries, we had no technical data on their power or current. The only thing we have figured out empirically is that we achieved a very good overall battery pack power, and we now know that each cell can deliver about 1 ampere. Not bad. In the second case, the 18650 batteries were surely very old and obsolete. They are probably more than 10 years old, so they definitely deliver less than 1 amp each. Modern batteries can deliver up to 20 amps of continuous power. Also, I only used 5, even though the board could hold 10, which would double the capacity and power. If we bought 10 new, high-quality, state-of-the-art cells, we could surely deliver far more power than the 68 watts achieved in the experiment. However, the problem is that each battery costs between 8 and 10 euros, and I don't want to spend that much money on one video, especially since I already had to buy the electronic load, PD trigger module, and other consumables.
That's why I created a Ko-fi account. You can support my videos there and help me become a rich and famous Italian.
As a reminder, all of the boards that I showed you in this video can be downloaded for free or purchased on my PCBWay page. You will find the link in the description. Thank you for watching. Subscribe to my channel and give me all your money so that I can become the Cristiano Ronaldo of YouTube when I grow up. Big hugs, friends. Ciao ciao.
Vabbè, non te vuoi fare din faccia. Meh, meh, meh.